All right, we'll get started here. Welcome to the Energy Symposium today. Next week's talk will be Neil McAndrews, who's a local economist in the area. He's going to talk about Georgetown, Texas, purchasing contract for 100% renewable energy, and what are all the sort of financial and contract details that go on behind the scenes to make something like that happen, so that we can have the context for, can everybody do that, right? This is just Georgetown, or can everybody in Texas go 100% renewable energy on a contract basis? So that's next week. So I think that'll be an interesting talk and to give us some insight into what goes on behind the scenes there. Today's talk is Matt Heun, who is a colleague of mine that I know because we have similar interests in understanding the role or thinking about how to think about energy and its role in the economy at the macro perspective. So he's going to give us some insights into that. He's from the engineering department at Calvin College in Michigan. But I know Matt has engaged with people who are thinking about this topic, primarily groups in Europe, in England, and in Portugal, actually, that are thinking about this topic on a fairly fundamental level. So he's going to give us his insights into thinking about the role of energy and macroeconomic modeling, which is his topic today. So, Matt, thank you for coming. Take it away.
Thank you, Kerry. Yeah, it should be on. And can you hear me all okay in the back there? Fantastic. All right, well, it is my pleasure to be here today, and thank you, Kerry, for that introduction. And I'm grateful for your presence here and for whatever interest you have in my topic. I hope that by the time we're done, your interest will be even higher. I'd like to start with a little bit of background on myself and by way of introduction. As Kerry said, I teach at Calvin College. It's in Grand Rapids, Michigan. We're a comprehensive liberal arts institution, and we were founded in 1876 by Dutch immigrants. We have a little less than 4,000 students, so a much smaller place than here, and of which about 500 or so are in engineering, and we graduate about 100 of those per year. We have a sustainability distinctive out of which much of my research flows. And if I were to summarize my current research activities and scholarship in a single question, it would be, what is the relationship between energy and the economy when viewed through the lens of sustainability? Now, some of my current work led to a paper with the same title as this talk, with some co-authors from the University of Leeds in England and the University of Lisbon and another colleague from Calvin College. And my goal today is to lead you through this paper. And as Kerry and I discussed options for what I might talk about today, this paper stood out because it's an example of data-driven analysis. And I hope that maybe 45 minutes from now, you'll agree that this was a good choice for the symposium today. So let's start by thinking about the economy through the lens of what's called neoclassical macroeconomics. Neoclassical macroeconomists think of the economy. Don't know where that came from. Think of the economy as though it were a transfer function, like you might have in an engineering class, okay? Inputs lead to outputs, which are consumed by final demand. In this world, in the neoclassical macroeconomics world, the inputs are called factors of production, and they are capital, K, and labor, L. And here capital means not money, but infrastructure, and machines that allow our economy to function. The transfer function that relates inputs to outputs is called an aggregate production function, or an APF, and I might use that acronym a few times today, APF. An example APF is the Cobb-Douglas production shown here, and it has an exponential, a coefficient here, an exponential term, capital and labor, and then these alpha constants here. Usually, the alpha constants sum to 1 for a constant returns to scale assumption, and the exponential term and its parameter lambda account for growth that is not well represented by the factors of production K and L. Lambda is named after It's called the Solow residual, named after the economist Robert Solow, who did a lot of early work on these kinds of functions. The factors of production and time are indexed either by ratio or by difference relative to an initial year. Now, a second aggregate production function called this constant elasticity of substitution production function is down here on the bottom, and it is both becoming more prominent and more popular in terms of use in macroeconomic modeling. It also has the leading coefficient, theta, an exponential term with a lambda in it. And it has the factors of production K and L, which you see here and here. But it also has, the factor shares are represented by deltas now instead of the alphas. And it has a parameter rho, which is related to the elasticity of substitution between capital and labor. So how easily you can change capital for labor in an economy. The Cobb-Douglas equation on the top is actually a special case of the lower equation, the CES equation, constant elasticity of substitution, when rho 1 is 0 and the elasticity of substitution between the factors of production is 1. We also have a third production function which we've dealt with. It's a baseline model, and it has the leading coefficient and lambda, but nothing else. So this would just assume that there's some kind of exponential growth going on. All right, what is missing from this picture? Constraints. Yes, there are constraints. That's not what I'm after right now, though, but good, good. We'll talk about constraints later. Yeah, we're at the Energy Symposium, right? Okay, perfect. Energy. Energy is missing from this picture. Now, intuitively, of course, energy is required for all economic activity. So how do we include energy as, the economists would say, a factor of production? Well, let's make room for it. And we have to add energy to our production functions. So there we've added it to the Cobb-Douglas equation. We have an additional factor of production, E now, which is energy, and an additional constant, alpha k. And then we can also add it to the constant elasticity of substitution production function down here, and that's a little bit more complicated. Plus, we don't know where to put it. Right, how do you know where to put energy in here? You've got one factor of production here, another one here, and we'll just throw it over here. And x1, x2, and x3 can be any of capital, labor, and energy. We'll talk more about that in a little bit. Yes, question? Yes?
What makes energy distinct from the capital and labor parts?
All right, so I'll repeat the question for the recording. What makes energy different from capital and labor? Aren't they interrelated? My answer to that is yes. Okay? But you could also ask the same question about capital and labor, right? What machines can you run without labor? Question in the back.
I guess to build off that, because I thought the elasticity, I'm not in economics, I don't really know, but you seem to make it sound like the elasticity is what connects them, and so why would energy just affect your elasticity?
Okay, you're asking, let me see if I understand your question. You're asking, doesn't the elasticity connect the factors of production, and why doesn't that happen with energy? Is that your question?
Yeah, so why would energy just change that elasticity?
Well, but you can think about energy as a factor of production replacing labor. So you'd want to have maybe energy substitute for labor. And so if we put, say, energy here and labor here, we would have an elasticity of substitution represented by rho 1 that would allow you to trade those two off against each other. All right? Is that helpful? If that's good enough for now, that's great, because we'll talk later more about these elasticities, okay? Awesome, but great questions. I love this. This is good so far. All right. Now, here's the thing about these aggregate production functions. They are used to generate policy that's economic and energy in nature. And we call this a theory to policy process. And it's used in the literature, in government budget offices, and at the World Bank, and probably lots of other places. And let me show you how that goes. In fact, the background that you have already on aggregate production functions is part of the first step in this theory to policy process, which is selecting a theoretical framework. The APFs without energy are an example of a theoretical pre-commitment of neoclassical economics. On the other hand, biophysical economics would say you need to include energy because all energy is required for economic production. So making a decision about that, about those two modeling choices, is part of selecting a theoretical framework. And you might have preconditions or pre-commitments from your theoretical framework that would put you in one direction or another for making those modeling choices. For the rest of this talk, I'll lead you through this theory to policy process, whose next steps are formulating modeling approaches, fitting to historical data, comparing and evaluating modeling approaches, interpreting the economy, and formulating policy. We'll do some economic modeling with aggregate production functions. And along the way, we'll discuss policy implications, we'll do some econometrics, and we'll encounter some cautionary tales. So if you're ready, I'm ready, let's roll, okay? But you know what? I forgot to get my glasses. I'm a new glasses wearer, so now I need to get these, and hopefully that'll make the talk even better. If I can see what I'm doing, right? All right. So the next step in this process is to formulate modeling approaches. Let's talk about what that looks like. These modeling approaches are a collection of modeling choices, and the modeling choices emerge from the complexities that lurk beneath the surface of these aggregate production functions. To illustrate what I mean, let's talk about the first set of complexities which arise when you think about just exactly what we mean about the factors of production. So, what is energy? This example societal energy conversion chain can help us think about that question. When we speak of energy, do we mean primary energy like natural gas and crude oil? Do we mean final energy that's sold to consumers like electricity, diesel, and petrol? Do we mean useful energy such as low temperature heat, light, and mechanical drive that is produced by machines that purchasers of energy own? And they buy that energy to get services from it, such as space heating, illumination, freight, and passenger transport. And ultimately, those energy services help to generate human well-being and satisfy human needs such as subsistence, protection, participation, leisure, and freedom. And then further, what do we mean? Energy or exergy? Exergy is the maximum amount of useful work that you could extract from a piece of energy. So do we want to quantify this as energy or exergy? And at which stage do we want to quantify our energy? We could summarize these issues in a table like I've done here, where I point out that energy could be measured in dollars, in energy, in exergy, at the primary, final, or useful stages. And for this paper, what we decided to do was to look at an unadjusted, or raw, and then an adjusted, or quality-corrected form of each of the factors of production. So here, our unadjusted version of energy is primary energy, crude, natural gas, and our quality-adjusted form of energy is useful exergy, the thinking being that the closer you are to the point of production in the economy, the more tightly linked your energy quantification and economic growth should be. But the complexity doesn't end with energy. You could think about capital too. Capital can be measured in terms of dollars, in terms of numbers of machines, say, in terms of the services that capital provides to industry. And we chose the volume of capital stock in dollars to be our unadjusted number, and the volume of services provided in dollars to be our adjusted number. These are concepts from economics that we tied into. And finally, labor. You could measure labor in terms of money spent on labor, the number of workers, work hours. We chose as our unadjusted measure of labor work hours, and our quality adjusted measure of labor to be education adjusted work hours. So to us, all of these options are worthy of consideration when we're trying to answer the question, what's the best way to include energy in economic modeling at the macro level? So thus, whether or not the factors of production are quality adjusted became a choice in our modeling efforts. Okay, the next complexity is which country and which temporal and spatial boundaries do you want to evaluate? And we chose to focus on Portugal and the United Kingdom because data are available for all unadjusted and quality adjusted factors of production, and in fact some of my co-authors are the ones who generated those data series. So they're readily available. And here's a table showing what they were from the paper. It's not a big deal, these lower ones, but I want to point out that for economic output we chose gross domestic product in US dollars, constant year dollars at power purchase parity to purchase power parity from the Penn World tables as our economic output number. So graphs of the historical data look like this. Indexed values of the various parameters all start at 1 on the vertical axis and increase from there usually. And the solid line is economic output or GDP. The long dashed line is capital. The short dashed line is labor, and the gray line is energy. So unadjusted factors of production are on the top row. That's these ones here. And quality adjusted ones are down here. Of course, we have Portugal and the UK there. One of the things to note is that there are some significant differences. Here's the capital line for Portugal. Quality adjusted, it's a big difference compared to the unadjusted one. The Portugal's energy line here is has a lot more increase in it than the UK's energy line does here. Interesting differences that will push our modeling in one direction or another. Okay, so the next piece of complexity comes from a thing called output elasticity and the cost share principle. This comes along with a theoretical presupposition that we are going to talk about in a second. And we choose the term principle. If you've ever encountered this in the literature, you would have seen people talk about it as the cost share theorem. But for us, a theorem has a specific if-then structure, and a principle can be applied to analysis. And we're interested in the principle here, but it comes from a theorem. So I'll make that clear in just a moment. Here is a formula for output elasticity. So you need to understand this before we talk about the cost share principle. And this is essentially the ratio of percentage change in economic output, Y, to the percentage change in each factor of production, X. So that's our ratio of percentage of changes is called output elasticity. Now the economic significance of this parameter, output elasticity, is that a larger elasticity indicates that the factor of production is more important to output than the other factors of production. One can also think in terms of constraints. If a factor of production has a high output elasticity, the economy can't grow unless that factor of production also increases. So thus, the factor of production with the high output elasticity is a constraint on economic growth. So for the Cobb-Douglas aggregate production function shown here, the output elasticity is just the coefficients, the powers on the terms. And in the Cobb-Douglas world, output elasticity is constant with respect to time. These alpha values are just constant numbers. On the other hand, output elasticities for the constant elasticity of substitution aggregate production function are significantly more complicated. And because these are functions of the factors of production which change over time, right? See how the X is in here? Then the output elasticities will also change over time. And thus, The CES aggregate production function can represent changing constraints on economic growth. And this is an important feature of the CES and an advantage over the Cobb-Douglas equation, which assumes that these constraints are constant with respect to time. Okay, now we're ready to discuss the cost-share principle. Rainer Kummel and some co-authors in a 2010 paper used the method of Lagrange multipliers to both prove and it had an elegant proof that showed where the cost-share principle comes from, and they showed why it has been assumed by neoclassical economists for so long. The theorem goes like this. If an homogeneous aggregate production function of degree 1, and both Cobb-Douglas and CES production functions are this way, if that homogeneous APF correctly models the effects of some factors of production on economic output, and here's the thing, there's perfect competition, and the economy is at equilibrium with no surplus or scarce resources, if, right, theorem, then the following cost-share principle applies. Output elasticity is equal to the cost share for each factor of production, where cost share is the percentage of GDP spent on that factor of production in the economy. Now, a key aspect of the cost-share principle is that historically, cost shares of capital and labor in developed economies are known to be relatively constant, as shown on this slide. So here's Portugal, UK, and labor is about 0.7, capital is always about 0.3. But the antecedents of the cost-share theorem, namely that there is perfect competition and the economy is at equilibrium with no surplus or scarce resources, those antecedents seem dubious at best, because we all know that there aren't really any equilibrium processes in nature in the real world. So for us, whether or not the cost-share principle provides a good explanation of any real economy seems worthy of exploration, and it is also a choice that we would like to make in our modeling as we formulate modeling approaches, whether or not to obey the cost-share principle. Now, one quick note here, because historical cost shares are relatively constant, any aggregate production function that obeys the cost-share principle must necessarily have constant output elasticities over time. Thus, the APF that obeys the cost-share principle is necessarily a Cobb-Douglas APF where those alpha values are constant. All right, the final complexity that I want to discuss here is constant elasticity of substitution nesting structure. And I'll show you what I mean by that. This table shows that 3 or 4 different types of nesting structures here, where K and L in parentheses means that we're going to lump those 2 factors of production together, and the third one, E in this case, we're going to leave outside. So when 3 factors of production are involved, these factors of production can occupy any of the 3 positions, and if we can either include or exclude energy, now we have 4 different production functions that we can look at, each having a different nesting structure. And so it's an open question in the literature, actually, and to the people and the co-authors on the paper, which of these is the best one to choose? So this is another modeling choice that we have. So all of these complexities, when taken together, can be summarized by considering several modeling choices. And these are whether or not to include energy as a factor of production, whether or not to assume the cost-share principle, which aggregate production function to use, whether or not we want to use our reference model, Cobb-Douglas equation, or the CES equation with its various nesting structures, whether or not to quality adjust the factors of production, and what spatial and temporal boundaries we're going to look at. And we made the choice to do Portugal and the UK from 1960 to 2013. Now, there are other modeling choices that are out there as well. That's not a complete list. For example, you could wonder about the quantification of economic output. We chose GDP at purchase power parity. we had one fitting procedure only. We'll talk about that below. But anyway, the collection of what choices you make on any of those options, decisions you make about those modeling choices, becomes a modeling approach. And I think you can appreciate that because there are lots of modeling choices, there will be many modeling approaches. Right? Do you see that? We get all different combinations of these things that probably ought to be evaluated and probably ought to be looked at. So after we formulate modeling approaches, we have to fit the equation that results from the modeling choices to historical data to determine the unknown parameters in the model. And this is essentially a curve fitting exercise, where after estimates of the parameters for theta, lambda, the alphas, the deltas, and the rhos, and I think you can see that we put all of our unknown parameters as Greek letters here. So it's worthwhile for a minute to discuss our fitting procedure, if only briefly here. And the goal is to fit these parameters and then use them later to interpret what's going on in the economy over time. So just for reference, I got the CES aggregate production function down here at the bottom. And some of the important features of our fitting procedure are, one, our objective is to minimize the sum of squared errors between the actual GDP that was observed in history and the prediction from our model. We also note that there are boundaries to the economically meaningful region for some of these parameters. For example, the deltas have to be between 0 and 1. The rho values have to be between -1 and infinity. The alpha values should sum to 1. That is the output elasticity, should sum to 1. Now when you put all those boundaries together, you get actually 20 degenerate boundary models, equations that describe the location of the boundaries. And so we fit along all of those boundaries as well. And especially for the most difficult parameters, which are rho and rho 1, we perform a 121-point grid search first, then a gradient search from the best point. And for each fit, we do two different gradient search algorithms, PORT and LBFGSB. So we haven't seen a fitting procedure that's this rigorous in any literature or papers that we've looked at. And we want it to be incredibly rigorous and very complete so that nobody could shoot holes at our work because we might have missed something in the fitting process. So here, for reference, are the 20 degenerate boundary models, all listed here. Now, it's important to fit along these boundaries because gradient search algorithms have real problems at boundaries. You often get close but don't get right on them, and we wanted to know if we were really at one of those boundaries. So we wanted to make sure we found them, and so we fit along each of these boundaries as well. Okay, so what we did is we fit all the possible combinations of modeling choices. That is, we fit all the different modeling approaches. And the results are shown in this figure. Each of the mini graphs represents a different modeling approach, that is, a different combination of modeling choices. And index GDP is on the vertical axis, time is on the horizontal axis. Historical data are shown as dashed lines, and fits to historical data are shown as solid lines. The rows here show the different aggregate production functions, and the columns represent combinations of country and whether or not the factors of production are unadjusted or quality adjusted. So some modeling approaches, like this one for Portugal, which uses quality adjusted factors of production and obeys the cost share principle, have not such great fits to historical data. But some, like this one from the UK, are nearly dead on. And if I back up a little bit, maybe you can start to see as we go down toward the bottom of the graph, they get a little tighter and better. But most fits are good enough that you can't even visually tell the difference between the historical data and the fitted function, because their sum of squared errors are nearly identical. You can get the residual, that is the difference between the fitted and the actual line as well. And so here's a graph, a figure showing residuals for every single modeling choice, some of which are better than others, of course. And we also performed bootstrap resampling to get a handle on the precision with which model parameters are estimated. In bootstrap resampling, we randomly pick one of those residuals and add it to the historical GDP to make a new GDP line, and we refit to that. And we do that 1,000 times. This refitting process gives us a resample distribution for all the parameters that we're estimating, all of the Greek letters. And this was really important for us because the usual methods for obtaining confidence intervals, how well you know the parameters that you're estimating, don't work very well when you have highly constrained fitting spaces. Boundaries are usually violated by symmetric confidence intervals. Yeah, question?
Observation on this. Do you think there's a reason why the models seem to have tighter residuals for the UK versus Portugal, or is that an assumption that you made?
Yeah, the question is why, the observation is that the models for the UK fit better than models for Portugal. And why is that? Did we make some sort of assumption along the way that would make that so? We fit both countries and all modeling choices with exactly the same procedure, so there's no assumption that we made anywhere that did that. It could be a data quality issue, uncertainty in the Y data that was generated out of Portugal, or it could be that the economy just is a little bit more random, more fluctuations. They also had a revolution, the Carnation Revolution, that didn't happen. The UK didn't have a similar event happen, so there could be any number of factors that are there. Okay, but boundaries are violated by symmetric confidence intervals, and we wanted to be very careful about that. And true confidence intervals for bounded fitting are often asymmetrical, and we wanted to be able to capture that asymmetry if it existed. So bootstrap resampling was an important technique for us to go through. So our resampling approach both respects the constraints and allows for asymmetric descriptions of parameter precision. And we did resampling and looked at these, the distribution of errors in the parameters for all modeling approaches that reject the cost share principle, that include energy, that use quality adjusted factors of production, and that employ the KLE nesting structure, just to get a handle on what was going on there. So this explains our process for fitting the data. And let's keep moving on. The next thing to look at is comparing and evaluating modeling approaches. So this figure shows sum of squared errors on the vertical axis and the value of lambda on the horizontal axis. And the use of unadjusted and quality adjusted factors of production is in rows, and the countries, of course, are in the columns. Other modeling choices are given by the symbols. Now, what you'll notice is that you'd like to be down on this graph. You want low sum of squared errors. You want to have a good fit. And you want to be to the left on this graph. Because if you're to the left, then your lambda value is small. That's just your general exponential growth term. And if your lambda value is small, then your factors of production, so here's your lambda value here. If that's small, then this term is close to 1, and all of your economic output is being captured and predicted well by the factors of production. So you'll notice here that on this graph, many modeling approaches have similarly low sum of squared errors, down, and which modeling approach is leftmost is not consistent. You have different symbols being the most left on there. So output elasticities, now this is where we get into the constraints question that somebody, or suggestion that somebody made earlier. Output elasticities are shown on the vertical axis on this graph and times on the horizontal axis. Each panel represents a modeling choice again, or modeling approach, comprised of many modeling choices. Countries and quality adjustment or not are in the columns, and the rows are the different aggregate production functions. Output elasticities for the top row are constant with respect to time because this is the APF that respects the cost share principle. But for those modeling approaches that don't respect the cost share principle, we let the output elasticity float with respect to time, and you can see that these all vary now with time. And we can pick up changing constraints on economic growth through this approach. So we'll talk more about that a little bit later. We generated resampling distributions for all of the estimated parameters for the modeling approaches that I mentioned earlier. This figure shows lambda, which is our generic growth term, against theta, which is our leading coefficient. And the crosshairs show us where our base parameter fit is. And all the other small circles all the way around give us the cloud of 1,000 points of resampled values for theta and lambda. And you can see that the confidence interval, if you could make a confidence interval out of this, the uncertainty bands are definitely not symmetric. So it's a good thing we did our resampling. I'll quickly spin through some of the other results. Here's delta and delta 1. You can see that we know delta 1 with a whole lot more precision than we know delta. This is elasticity of substitution. This is the value for sigma. And you can see that over here we know it pretty tightly, but over here we don't know it very well at all for Portugal. And then, of course, if you resample the elasticity, the output elasticities, you get 1,000 different lines for each of the possible output elasticities. And so we're showing those here for Portugal and the UK. And you can see significant lack of precision in understanding where these things really are. Okay, so that's comparing and evaluating modeling approaches. And now we get to the main event, interpreting the economy and formulating policy. So these last two steps are important because historically, for example, large values of the Solow residual, that lambda parameter, were taken as a mandate to increase spending on technology and technology development in Western societies. For China, interpretation of the economy in step 5 included indications of large values for capital's output elasticity. Alpha K was high. So the World Bank used that as justification for supporting infrastructure spending in China in the 2000s. In our paper, we addressed steps 5 and 6 by picking off a few examples from the data that I just showed you and running through the process of saying, okay, if this is what the results show, then what would that imply for policy? And the first of these examples involves the United Kingdom and nesting structure for models that reject the cost share principle and employ the KLE nesting structure. So here's the data on all of the output elasticities. If one assumes the capital labor energy nesting structure, then this figure of output elasticity shows that alpha E, which is the gray line here, was flat and low and then all of a sudden jumped up to be almost 1. And it moves up to 1 at about 2008, which was the onset of the Great Recession and the 2008 peak in oil prices. This transition occurred for both adjusted and unadjusted factors of production. And here's the details of that. Furthermore, the transition to large alpha E is consistent for all 1,000 resamples. Now, the economic interpretation here is that a structural change has occurred in the UK economy. Energy is now the dominant constraint for UK economic growth. Energy has become key to the UK going forward, eclipsing both capital and labor in importance. And furthermore, the sigma value, that is the substitutability between the capital labor composite and energy, is super low. It's down here at the bottom of this graph, indicating that you can't substitute capital or labor with energy. So the policy implication from all of this, from a new understanding that you get from the economy by interrogating these results that you get, the policy implication is that deep investment in energy, as opposed to capital and labor, is needed to relieve the energy constraint and to return the UK to economic growth. Now, a plausible energy-related narrative can be constructed around these results. The narrative is focused on resource depletion concerns and is biophysical in nature. Worldwide constraints on oil supply that began in 2003 led to the oil price spike in 2008 and contributed to the Great Recession. For the UK, these events all transpired about the same time that North Sea oil and natural gas production peaked in around 2000. And that deepened dependence on expensive energy imports of oil and natural gas into the UK, and that's going to continue going forward. note that these blue production lines are dropping below the red consumption lines, meaning that the UK is now an oil and gas importer. In this narrative, these trends altered the fundamental structure of the UK energy economy nexus, and today the UK needs more than anything else to invest in energy to sort out this constraint and reignite economic growth. The problem is that if one assumes the LEK or the EKL nesting structure, we find that the output elasticity for energy, the gray line, is always low for these ones. There's a narrative that can be constructed here as well, and it's focused on long-term versus short-term effects. Economists generally agree that demand-side factors such as energy and energy availability have an effect on economic growth in the short term, but in the long term, it's production-side issues that are really the long-term constraints. So they're mainly constrained by factors that influence aggregate supply, such as investments in capital, infrastructure, human capital, which is labor, and then technology, which is the lambda term. If the results of these two nesting structures are to be believed, then they can be taken as indicators as long-run performance, and you can think that despite experiencing transient distortions in demand, the UK should really be investing in labor or capital and research and development to transform its economy and achieve sustainable economic growth over the long run. Now, yet a third narrative can be constructed around this information. And it comes from the a priori assumptions of neoclassical economics. This narrative might be called the CSP narrative, and it emerges from the pre-commitments of neoclassical economics. If the assumptions of that sort of theory are to be believed, then one expects output elasticities to mirror the cost shares in the economy. We talked about that before. And modeling approaches wherein the cost shares most closely approximate the output elasticities are to be preferred. And we see that among these modeling approaches, the one that comes closest is this, and here's the historical data. Thus, the assumptions of the neoclassical framework, but not the data or the empirical results necessarily, will lead you to rejecting the KLE and EKL nesting structures in favor of the LEK nesting structure here. The policy implications arising from the neoclassical approach are that we need to have minor investment in energy, more investment in capital, and a lot of investment in labor, because alpha E is less than alpha K, which is less than alpha L. Now here I'm showing the fitted solid lines and historical dashed lines versus time for the three different nesting structures. And the three narratives are, and there's the residuals too, the three narratives are depletion, which supports the KLE nesting structure, short-term demand, long-term supply, which can support either of these two nesting structures, and the cost share principle, which supports the LEK nesting structure. These narratives are not clearly differentiated by the data or the results. Thus, there ought to be significant uncertainty regarding which energy economy policies should be followed. Yet, if you choose your nesting structure a priori and don't look at the other ones, you will get a very clear policy prescription, even if examination of the other options would have sent you in a different direction. Okay, cautionary tale number one then is that very different narrative-supported energy and economic policies can result from upstream modeling choices that may have no a priori mathematical justification, like the KLE, EKL, or LEK nesting structures, and are poorly differentiated in the data and in the results. A second example, and this one will be shorter, comes from Portugal, and interpreting and formulating policy when you're investigating whether or not to quality adjust the factors of production. If we look at the KLE nesting structure, which is right here, we see that output elasticities have similar shapes, but different magnitudes depending on whether the factors of production are unadjusted or quality adjusted here. Here's what they look like in some detail. If one assumes unadjusted factors of production, that is, and you would see that alpha E, the energy output elasticity, is about 0.35, and it's relatively constant over time. So you would say that the economic interpretation would be that energy is important for future economic growth for Portugal, although not as significant as labor at this point, this short dashed line, because it's higher. But because there's a large value for the sigma, you could substitute energy for capital and labor for energy anyway, so this energy probably would not be a very significant constraint. However, if the upstream modeling choices was made to quality adjust the factors of production, then you have even less concern. So which one you choose is going to determine how much concern you have about energy being a constraint on the economy. However, bootstrap resampling shows that we have significant uncertainty in the range of these values anyway. And the policy implication here would be that we should focus on labor today because it's way up here, but you have to temper that prediction based on how uncertain these values are for your output elasticities. We don't really know these things very precisely at all. All right, so our second cautionary tale is that different policies for the balance of investment between energy and labor could be suggested depending on the upstream choice that you make for whether or not to quality adjust your factors of production. And imprecision in the estimates for important parameters can lead to uncertainty in policy prescriptions. But you wouldn't pick that up unless you did an uncertainty analysis. All right, now some concluding thoughts. This paper is, in fact, the latest in a long line of papers to question the wisdom and validity of modeling whole economies with aggregate production functions. But this paper adds a rigorous analysis driven by data as free as possible from a priori assumptions. Indeed, my co-authors and I haven't seen a paper that clearly identifies the theory to policy process and unravels the modeling choices in this space and evaluates all of the modeling choices and uses a rigorous fitting procedure and performs bootstrap resampling to estimate parameter precision and considers the policy implications of comparing all these modeling approaches. So putting all these things together, we find for our examples that both interpreting the economy and formulating policy can change substantially under alternative modeling approaches that are not a priori suggested by the mathematics. And furthermore, for the countries and years that we studied, many modeling approaches are not differentiated well by the data or by the results. Now, the theory to policy process is not merely an academic thing. Like I said before, it's used worldwide, and the policies that it generates affect economic development and quality of life for people everywhere. Like all modeling, fitting APFs to historical data is by necessity a simplification of the complex world in which we live. And it's fraught with perils, including the following circular truths. Our understanding of reality shapes our modeling choices. And our modeling results affect our understanding of reality. So given all that, we provide several recommendations. Now, many of these recommendations are common sense, but if they're not initially obvious, hopefully our examples will have convinced you that we should do some things very carefully here. First, analysts working in steps 2, 3, and 4 must take great care. In particular, those folks in step 2, we recommend that they evaluate the impact of a wide set of modeling choices. They don't just launch down one road. And the analysis that I presented today may provide a template for doing so, at least expanding that space a little bit for people. In step 3, we recommend widespread use of techniques to estimate parameter precision beyond confidence intervals determined from standard error, and maybe our resampling approach can help with that. In step 4, we recommend that analysts communicate clearly what modeling approaches were considered and the criteria with which preferred approaches were defined. And a reciprocal responsibility exists for those operating in step 5 who need to be very aware of the upstream modeling choices that were made and how their interpretations are going to be used to formulate policy. So we recommend that those operating in steps 5 and 6 demand clear and transparent communication from those operating in earlier steps. Taken together, these cautionary tales lead us to a final cautionary tale, perhaps, and it's this. It's possible that energy economy modeling with APFs tells us more about theory and modeling approaches than about the economy itself. If so, this conclusion is both uncomfortable and undesirable, given the pressing need to formulate effective energy economy policy to address resource depletion and carbon emissions problems without harming economies worldwide. So it's a dangerous modeling world out there. Be careful. Thank you for your interest and your attention and your good questions already. That's the end of my prepared remarks, and at this point I'd love to hear comments and additional questions if you have them.
Questions, anyone? Further questions? No? So I'll ask a question then. I guess the question is the cautionary tale, it's the broad question. Should aggregate production functions exist as a thing, I guess? Is that, that's a tough cautionary tale. Is that one of these, right? I don't know. Do you have further thoughts on that?
Yeah, okay, that's a great question. Should aggregate production functions exist? I want to be careful that we're not doing too much of a generalization here. We looked at 2 countries over short time periods, right? And so it's certainly not true that it's universally clear and accepted which modeling approach should be used when you're adding energy to an aggregate production function. And it's not clear that the data and the results would tell you what policies ought to be pursued for the countries I looked at. So you can't say that it's universally clear that this is the best way to go. You would need to study essentially many more countries and look at many more situations in order to decide whether they should exist at all or not, to be fair. I personally have decided to go in other directions on my research and not sort of focus too much on this anymore, because I'm not sure that there's a whole lot of there, but we felt it was important to document what we found and to raise questions for other people who might be working in this space. Is that a reasonable answer, do you think?
Yes, yeah. I personally think it's good for people that felt the need to go through this process to present that I went through this process and here's what I found out and how useful I think it is, instead of not documenting it so that no one knows. So I think it's very useful.
And it was a bit of a challenge, too, to find, we had other objectives for this. We were hoping to find the best way to do this and be able to share with the entire world, this is how you do it now, and you're going to use exergy, and it's going to all work out. But it didn't turn out that way. And so what do you do in that case? Well, we made a little bit of lemonade out of lemons here and turned it into cautionary tales, which I think is an appropriate way to go. But I think it's also really worthwhile the last thing that I said there is that there's always this circular truth that you are, the choices you make about the way you model stuff is affected by what you already believe about the world. And the results of your modeling affect what you believe about the world. So you just always go around in this cycling. And I presume there are many graduate students in the audience here, and as you are doing your modeling work in whatever sort of realm, whatever APFs or not, you have to be super careful about that you're not trapped in a situation where you've made an assumption that necessarily will come true in your results just because you made that assumption. And that could be a dangerous place to be.
Wait for the mic.
Wait for the microphone.
Thank you, Dr. Heun, for the great lecture. My question is, have policymakers in kind of London or Portugal kind of seen your conclusions and kind of considered the importance of increasing energy consumption and taking that into consideration for their policies?
I am not aware that any, okay, so back up. My contacts and my co-authors in Portugal and the UK have been and are involved in like Eurostat and other conversations, World Bank conversations. I honestly don't know if they have talked to their contacts in Eurostat or at the World Bank about the results of this particular paper. It came out just earlier this year, and I honestly haven't even asked, so I'm not sure. I guess maybe that's an encouragement to me to go to ask the question and encourage them to do that, because one of the things I didn't mention is that some of you may be involved in general equilibrium modeling or whatever, where if you dig deep enough down into the levels of the model, somewhere down in there might be an economic aggregate production function that's being assumed that takes these aggregates of capital and labor or some other resources in the economy and then projects forward to economic growth. And so you have models like this that are embedded in larger models, and the larger models can sometimes obscure the complexity of the larger models can obscure the fact that buried deep inside them is one of these equations that they've made assumptions about what the parameters ought to be, and then they just run with it from there. I know there's a lot of climate models that does, integrated climate economy models do that. So that would be a place to intervene and have an impact. Yeah, great question. Thank you.
So it seems like early on when you prescribe what energy is, you kind of pick the natural gas and crude path. And I guess I wanted to know how the model accounts for shifts in the energy paradigm. So let's say it's not just natural gas and crude in 20 years. What's the reliability or maybe sensitivities behind the model if something like that is introduced into the economy of Portugal or the UK?
Okay, that's a great question, and I think you're being sent in that direction because one of the diagrams that I showed had crude and natural gas in it, followed by final energy, which would have been refined petrol and electricity, followed by useful energy, mechanical drive, and so forth. All right, so let me be 100% clear. That diagram was simply to illustrate the idea that there are different stages of energy and then different quantifications, energy or exergy. When I showed you the graph that had GDP, capital, labor, and energy as a function of time, so our sort of input variables. Those, in fact, let me just go find it here because I want to be perfectly clear. It'll take me just a second to get there. Yep, this one. These lines on this graph include all types of, for the unadjusted one, all types of primary energy aggregated together. That's why it's called an aggregate production function. You aggregate all those, the gray line is all types of energy aggregated together. And similarly on the bottom, the quality adjusted row there has all types of useful exergy aggregated together. So we've accounted for any shifts that have happened from 1960 to 2013. In different modes or types of energy. Now, that's one of the criticisms of aggregate production functions is that they don't have any discrimination amongst different types of the aggregated input. So a BTU or a kiloton of oil equivalent or a gigajoule of oil is the same as a gigajoule of coal when we're talking about the unadjusted row up here because those are the primary energies. And down here, when we have useful exergy, a gigajoule of mechanical drive spinning shaft is equal to a exergy adjusted megajoule or gigajoule of low temperature heat to heat houses and stuff like that. And so, so that's a necessary approach to using aggregate production functions is to aggregate all your inputs together. But another great question. Thank you.
Anything else? Nothing else? Okay, I thought that was a great talk, an overview about how these things are actually kind of formulated a little bit from the ground up in a short period of time. So I think it was a great job. So thank Matt again for coming to the symposium. Thank you very much.
Thank you.